Big idea is that you just need to learn some more tricks. You actually already have all the content knowledge to do well with these U substitution questions, but now we have to add a little bit of that algebra stuff in here behind the scenes. So a question like this looks damn near impossible to begin with, but you can also make it a lot simpler. Number one thing to do, if you have a fraction with a single term on the bottom, split that bad boy in half so that you have cosine cubed of x over cosine squared of x, and then you have sine squared of x over cosine squared of x. It looks something like this. Two separate integrals completely. One of the rules of integration is that if you have a plus or a minus separating the terms, you can actually make those completely separate integrals for which you will find the evaluative solution independently. From here, simplify it down a little bit. For the first one, you just have cosine of x dx. Remember, you got to have the dx because it unlocks the power of the antiderivative. But for the other one, the question is, should you make this one tangent squared, or should you do something else to help you simplify it down? Me, Nura, and Brett sitting here a second ago, we tried to make it tangent squared, failed. Don't know the antiderivative of tangent squared. But a trig identity can come into play right now by changing this thing into 1 minus the cosine squared of x over the regular cosine squared of x dx. Then you take note of the fact that it is actually another fraction that has a single term in the bottom. So you need to perform that same separation again. She says, oh God, and no at the same breath, but we have to do it that way. First one is going to be 1 over cosine squared of x. I smell another trig identity coming. The next one, minus negative cosine squared over cosine squared, is really going to become plus 1 dx. That trig identity I was referencing a second ago is that you have the cosine squared on the bottom. When cosine is on the bottom, you can turn it into the secant. Brett says I'm supposed to make it minus, but again, it was a minus negative cosine squared. So take that, Brett. Hope you're enjoying Amsterdam when you watch this live and direct on the computer. Yeah, you know, Brett's got to watch it twice. You know, he sometimes he thinks fast, but this time he was thinking slow. Goodness. Time to do some antiderivatives. Antiderivatives on this particular set of integration is going to have three different parts. You've got the negative sign, no, positive sign, my bad, minus the tangent plus x, and finally c. And you got to have that plus c at the end. The plus c is the plus a constant. It's because this is a general solution. It is a family of solutions, not just one particular function. We're going to do another trick, but I got to set that thing up. Where's the pause button? All right, problem number 2. Talking about more tricks. It's actually the same trick again. It's just going to manifest itself slightly differently. The first time we were talking about a fraction that had the same simple denominator, so you split it up. Problem like this, same thing. Split it up. There's no difference between the question that is given to you with the cosecant squared of 4x plus 7 with the dx here compared to what you get if you separate them. The reason why I like to separate them, main reason is because it allows you to see that U substitution a little bit more clearly. This U substitution, this particular time is one where we actually have to manufacture that du to fit better than what we're given. Like when you look at the inside of this cosecant, you know that your u is supposed to be 4x plus 7. But du in this situation is supposed to have a 4 in it that we don't have. And if you had left it the way that it was originally, multiplying that extra 4 in there was impossible because it would have affected your 2x as well. But that's why we split it up. It's because now when you want to go and manufacture this 4, you want to put it right here. You can actually put that 1/4 on the outside. Remember, the reason why you have to put the 1/4 as well is because if you only multiply times 4, you change the value. You change the relationship that it's talking about. You've got to preserve it by multiplying by 1. 1/4 times 4 is 1. The other integral over there, the 2x, stays the way it is. Nothing special has to happen with that. The u substitution, though. Now I'm looking at 1/4 of the cosecant squared of u du plus the integral of 2x dx. And Nura says, but I got u's in the first integral, x's in the second integral. I'm supposed to change all the variables, but remember, you're going to change it back to x's later anyway. Don't worry about it. We only needed the u substitution for that first integral, which is why we separated it in the first place. I asked Brett a minute ago, so he better get the answer right this second time. What's the antiderivative of cosecant squared? There we go. We have a negative of 1/4 times a negative cotangent of u plus x squared plus c. Can't forget the plus c because we're doing indefinite integrals. Later on in the semester, we'll start doing these things called definite integrals, which I was just talking to my two friends here about a second ago. It's what happens when we actually have boundaries. Right now, we are boundaryless, and that is a comfortable place for us to be. Boundless. What a good word. I am unbounded. You know what? Let's go ahead and combine these u's back in with the x's at this point. And once you have everything compound, you will be completely done. Yeah, that's another word that doesn't exist. And it makes no sense. Why not? Compound should absolutely be a word. The classic What Face by Ryan DeCillo, as referenced by Brett Lucas. Man, that's deep. That's some tough stuff right there, Brett. I gave you the second derivative on this one for a reason, is to mess with your mind a little bit. I also made it so that Nura, you couldn't just go and foil it in a comfortable way, right? Like you could, if you really wanted to, multiply 2x minus 5 times 2x minus 5 times 2x minus 5, then do the antiderivative of all of those different terms, making sure that you didn't mess up any coefficients, and then do the antiderivative a second time because this represents a second derivative, or we can use our new u substitution to help us out a little bit. Having said that, u is going to be 2x minus 5. So essentially what we're doing in this particular problem is, yeah, we need to separate our variables, which is the first step. But when we make this other side, Brett said go ahead and make it a u instead. Make your life a little bit easier that way. So we're going to have u to the third power du, but was your du complete? Yeah, that's the problem with doing so much stuff in your head, Brett, is that you missed out on the fact that your du is supposed to also have a 2 in it because of that chain rule. From the 2x minus 5, that 2 needs to be included. I'm going to include it in here. I'm going to put the 1/2 there for you. right now. I'll show you that step the second time we go through this problem for getting all the way back up to the particular solution. From here, apply your integral. Boom, boom. The antiderivative of the second derivative is actually the first derivative. Let me break that down to you one more time because your face says that you have no idea what I really just meant. The antiderivative, so going backwards from the second derivative, so starting with derivative number 2, double prime, you just end up at single prime, not all the way up at y. It does make sense. You just got to say it kind of a little bit slower. So you just have dy over here. On this side, antiderivative says that you make this u to the 4th power over 4. That 1/2 is still there, plus c. There's still going to be a dx there, but we can hold off on that for a second. F prime of 0 is 3. Plug this information in. At this point, we need to use our first initial condition. It says that y prime is equal to 3 when x is 0. Means plug in 0. That means your c value has to be 3. You're not an idiot, Brett. You figured it out, and that's all that matters. That was like 7 minutes ago in the video. It's okay. He's grown up a lot since then. Only in the academics, not in the height, though. All right, so I'm going to take this, and I need to do a second derivative on it. So what I'm going to be saying is that dy is now equal to 1/2 of u to the 4th over 4. Let's change that to just u to the 4th over 8 plus 3. Oh, shoot, I screwed up. I screwed up, y'all. You didn't catch my mistake either. The mistake that I made is that we are supposed to be plugging in x's, not u's. So c is not actually going to be 3. We need to take this and plug it back in. Yes, Lord. This is going to be 2x minus 5 to the 4th right there, plus c. Still plugging in 0, so 5 to the 4th is going to be 625 over 8 plus c. It's got to equal your 3 on the other side. C this time is going to be, c is going to be negative 601 over 8. Yikes. Brett's still mesmerized by the mathematics I did in my head. 5 squared is 625 over 8 on this side. At the other side, it was 3, so that's 24 over 8. Subtract it away. That's how we get the negative 601 over 8. Brett loves me, but he also hates me. Noor was chewing on a paperclip and lost it. We got 1 minute and 20 seconds left in this video, y'all. So let's keep this thing going. Now that we have a dy with the proper variables and the proper c, which I screwed up on originally, this thing says 2x minus 5 to the 4th power. All of that is over 8 minus 601 over 8 dx. Remember, that first derivative got rid of one of the dx's. We still have another one to worry about at this point. Antiderivative again. But this time doing that antiderivative, notice that your u, the 2x minus 5, is missing that 2 again, Brett. So if I want to bring that 2 in, I'm going to have to change this thing a little bit. I'm going to make it u to the 4th over 16 because I want to make sure that I had that 2 from my 2x minus 5. Earlier in the video, we said split it up if you want to. If you don't want to, you don't have to. Antiderivative turns into this. This right here with your plus c at the end plug in your values one more time, you end up with C